So we're going to talk about crystalline solids. Remember that crystalline solids have long-range order and in their molecules or atoms. These form beautiful crystals. Here we have, I should look up what that is. I think it's quartz, not sure. Here's a close-up of a snowflake. You probably are familiar with the idea that snowflakes always have 6 sides, and that actually comes from the crystal structure of the water molecules as they freeze. They form hexagons. So we see these beautiful, beautiful shapes, and all of those come from the organization of the atoms and molecules in those structures. And so we're going to look at what those types of organizations are. So how do we figure out how atoms or molecules are organized when they're far too small to see? We use X-rays. So X-rays are a form of electromagnetic radiation. They just have much shorter wavelengths than visible light. And so we need to review and remember about interference in electromagnetic waves. So you can have constructive interference and destructive interference. When 2 waves are in phase, they interfere constructively. You can think of them as adding together, and they add up to have larger amplitude. Destructive interference comes when you have 2 waves that are out of phase, interfering with each other, and they basically cancel each other out. Remember the video we saw with the guy in the big cardboard box he took out on the beach? And we saw the diffraction pattern? That's the idea we're talking about here. So the waves interfering with each other create a pattern. So we can do this with X-rays because within a crystal, the distances between the atoms are about 100 picometers, which is about the wavelength of an X-ray. In order to get diffraction through slits, you have to have that slit distance about the same size as the wavelength. So X-rays are perfect for this. So we can look at the spacing between the layers of atoms or molecules in a crystal using X-rays. You take an X-ray source and you get a beam from that and you hit a crystal with it, and as the X-rays go through the crystal, it's like they're passing through slits within the crystal and they form a diffraction pattern. By analyzing the diffraction pattern, you can figure out what the distances are and the organization of the atoms or molecules in the crystal. It's a lot of geometry. We're not going to go into big detail about that, but we'll just talk very generally here about what happens. So when an X-ray beam, so you have individual rays, and if they're coming from the same source, they're going to be in phase. So these are coming through in phase. We'll try to draw one here. So this is peak 1, peak 2, peak 3. And you'll see that this one I've attempted to draw in phase. They're coming in with peaks aligned. When they hit this crystal, they will bounce off of the particles in the crystal. So here's one atom, and this ray hits that atom, bounces off, and it's going to have a particular phase as it comes off. This second ray doesn't hit directly in the first layer, so it hits on the second layer and bounces off. So this traveled a little farther than the first one. This one bounced off the surface. This is bouncing off the second layer. This distance A, from here to here and from here to here, it traveled 2A farther than ray 1. Does that make sense? And so we can end up with it still being in phase, 1, 2, and 3, but now that one, because it had to travel farther, is delayed. So the peaks are still matching up, but they're not the same peaks. We don't care about that. We care about, are they in phase? They will be in phase if this distance, A plus A, 2A, the path difference, if that equals some integer multiple of the wavelength. If this is equal to 1 wavelength in difference, then they'll line up like this. 1 will line up with 2 and 2 with 3, etc. If this 2A is equal to 2 times the wavelength, then this peak 1 would line up with peak 3. They'll still be in phase, but they're offset. Does that make sense? So we can do a little geometry here. We want that 2A distance to be equal to some integer multiple of the wavelength of the radiation. And then we can use trigonometry. That tells us the sine of that angle theta is equal to A over D. So we can rearrange that. A equals D sine theta. And since 2A equals n lambda, then we get n lambda equals 2D sine theta. You do not need to derive that. You do not need to remember that. But you may have to do a calculation or two using that equation. It's called Bragg's law. Any questions? N lambda equals 2D sine of theta. The way X-ray crystallography typically works is that you vary the angle at which you're shining the X-rays on the crystal, and then you can figure out at what angle am I getting constructive interference. And from that, you can get the distance. Remember, the distance is the difference, the distance between the two layers of the crystal. So you can rearrange Bragg's equation for distance. Distance equals n lambda over 2 sine of theta. X-ray crystallography is used to analyze lots of different things. It was X-ray crystallography that led to the discovery of the double helix structure of DNA. It's just pretty cool stuff. This is an early picture of an X-ray crystallography data. And you can see, looking at that, you're like, what the heck? How do you get anything out of that? But the scientists can get stuff out of that. You can find the, anyway, you just can't. I am not at the top of my game today. Okay, let's do a calculation using Bragg's law. So we're told that the spacing between layers of molybdenum atoms, that's just a hard one to say, molybdenum, is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So we need Bragg's law. So n lambda equals 2d sine of theta. They're asking us to calculate the angle. So we could rearrange this. The sine of theta will equal n lambda over 2d. Just took this equation, divided both sides by 2d. So the sine of theta, sine of the angle, equals this number. Well, we have to identify what are these different things that we've got in here, these different variables. Well, n equals 1. We've just flat out said that. And then the spacing between layers, what variable does that correspond to? D. So D equals 157 picometers. And 154 picometers, what is that? That's lambda. That's the wavelength of the X-rays. So we have n, lambda, and D. We just need to plug them in here. So n is 1. Lambda is 154 picometers. Always write the units in. 2 times D is 157 picometers. And we see that those units cancel out, picometers over picometers. So we don't have to convert them to meters or centimeters or anything special. But they do need to cancel out. So this gives us a value. Oh, I forgot something. Calculator. This gives us a value that is going to be the sine of theta. So 154 divided by 2 divided by 157, 0.49044. 5/86. But we want sine of theta. I mean, we want theta. We have sine of theta. We have to do inverse sine. So that was sine of theta. Theta will equal the inverse sine of that number.
29.36.
Yeah. Blah, 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 44586. And so it comes out to, is it 29.4? 29.4 degrees, because angles are measured in degrees. Unless they tell you you're dealing with radians, but we don't do that in chemistry. Yeah, I don't like radians. Stupid. Sig figs on this, you can't really do sig figs, so just try to be reasonable. I figure, well, these things have 3 sig figs. Given 3 sig figs here is reasonable. Giving 10 digits is not reasonable. Giving 1 is not reasonable. It's better to give too many than not enough, but don't go overboard. Any questions?